So let's see, today we're going to continue with waves by talking about light. We're just going to go straight into light. I think we did enough with sound and speakers. If you do the homework, you'll be well versed in sound interference. But now we've got to talk about a new kind of wave called light and how we can get interesting optical effects, interference, etc. Alrighty, hello, this is a reminder. Oh, no, that's not you. Something else. Okay, so light is very interesting, and people have wondered for thousands of years what it is, and we would know what it is. But there's still three different ways we think about light. Three models of light, okay? The first, well, not historically, but the first is that it is a wave. And that's what we're going to do today, the wave model of light, because we're talking about waves. The second is that it is a ray, right? A ray of light. Sounds familiar. A ray just means a line. So you don't even worry about the fact that it's oscillating. You don't worry about its amplitude. And you don't even worry about its phase. You just draw a line. This is the old version of light. And it's actually, you can describe quite a bit of optics with just the ray model, like our glasses and everything. So we're going to do that as well, because that's the macroscopic. And then there's this one, a particle. And there was a big, long confusion in quantum mechanics. Is light a wave or a particle, and back and forth, and which is it? And the answer is it's a particle. Okay? But to understand the particle nature of light, you've got to study physics for like 10 years just to not understand it. Okay? And then another 10 years, and then you can understand what a photon is. So we're not really going to talk about the particle that much. I mean, you can just say, it's a particle. I understand it, but to really know why you have to describe it as a particle that is a quantization of a classical field, it's very complicated. So today, waves, and then next week we'll be getting into rays, okay? Geometrical optics. Okay. So today, wave model. Here we go. Light is a wave. I've got 6 happy facts for you about the wave model. Just some things, so we're not going to derive full electromagnetic theory and prove all this. We're just going to tell you a little bit about how light works. Okay, number 1, light is a wave. That sort of goes with the why it's called the wave model. But of what? Of the electromagnetic field. If we were doing this in proper intellectual order, we would do the electric field first, and then the magnetic field. And then we would realize, oh, light is a wave of these things. But I'm giving it away now. It's a wave of both the electric and magnetic field sort of oscillating together. Okay? Field. But that's really the only difference from what we've been doing at the level we're going to do this. So we talked about waves where the amplitude was the pressure for sound, was deflection for the string, was the surface of water. Now it's literally just E. So we can even just focus on the electric part and not worry about the magnetic part. And we could write the wave like this. E equals E naught. All right, so this is the E field is a function of space and time, just like the string. This is the amplitude of the wave, sine, and guess what? It looks very familiar. Kx minus omega t plus phi naught. So just like all the other waves we've been doing. And just like the other waves, we talked a little bit about plane waves and spherical waves, so light can do all those things. We're usually just going to describe light as sort of a 1D wave. We're just going to draw this and not worry about the 3-dimensional part as much. Okay, so we're really talking about plane waves, where you have the E field going up and then down and up and down, like a plane moving forward. But this basic happy fact is just, it's a wave. Okay, here's another one. Oh, I can't draw. Light has a very high frequency. High frequency. So roughly, how high do you think it is? 10 to the 14 hertz. Can you imagine 10 to the 14 hertz? No, you cannot. Okay, 10 to the 14, very big number. 10 with 14 zeros. And a short wavelength, right? And that, yeah, you could imagine that. Here at Rice, where everybody's forced to think about nano all the time, you can envision 1 micron. Right? That's like 1/100th of the width of a hair, something like that. So the wavelength is sort of in a physical scale that humans can imagine. This you can't. You can't think about 10 to the 14. And then related happy fact, while we're just impressing you with numbers, it travels very fast. Very fast. Let's see. It's such an important number, we abbreviate it C because it shows up in physics all the time. And it's the well-known 3 times 10 to the 8 meters per second. 3 with 8 zeros. Pretty fast, a little hard to envision. The most standard descriptor that helps you envision it is that's going around the Earth 7 times in a second. So pretty fast. You could sort of imagine that if you've flown, partway around the Earth. Let's see, what else do we know about light? Okay, so those are sort of the basic ones. Now let's get into the slightly more detailed properties of light here. It slows down in a dielectric. Oh. What? I thought the speed of light was constant, universal. Slows down in a dielectric. And what the hell is a dielectric? So a dielectric is just an insulator like glass. And usually you think of ones that are transparent where the light doesn't scatter around inside, the light just goes right through. So dielectrics, fancy word for glass, or air, or water, or plastic if it's clear, etc. Okay? So the speed the light goes in a dielectric is the speed of light, and you just slow it down by a factor n, or n is the thing you maybe heard of, the index of refraction, which we'll use later when we get to geometrical, or when we get to the ray model. So light does slow down. It doesn't go 3 times 10 to the 8 in glass. It slows down. It's not really slowing down in the constant of the universe sense. It's that the way the light interacts with the matter and the scattering all adds up, and it looks like it's going forward at a slower speed. In between the atoms, you could say it's still going the speed of light. But that's a very weird thing to say. So it slows down. It also gets a shorter wavelength. So it goes down also by n. So the wavelength gets bluer inside the light, which is kind of weird. What else does it do? Yeah, that's the main things. So here you'll see I wrote something important here. I put a naught on this. So lambda naught is what we call the vacuum wavelength. Okay? So in vacuum, the speed of light is 3 times 10 to the 8. So that's why we always put C when we mean in vacuum there. But if we start quoting wavelengths in other problems, if I say, okay, some light goes into some glass and its wavelength is 500 nanometers. Well, what do I mean? Do I mean 500 nanometers in the air, or do I mean 500 nanometers in the glass? Right, so that's how we specify the difference. Lambda naught always means before it goes into the other material. And to make it a little more confusing, let me show you some index numbers here. So vacuum, why we call it the vacuum wavelength, n equals 1. Air, n equals 1.000, I meant to look it up, 1. I think it's 3 zeros. Okay? So the index of air is almost exactly the same as vacuum. So if you want to call it the air wavelength, you can. Okay? But it's basically, I say light goes into some glass, it came out from the room. The room means it was in air in the room. Basically, it's the vacuum wavelength. But in the glass, it's going to drop by quite a bit. Because n for glass, thank you for that transition, is n equals 1.5. Okay? So now that you have a number, you can see, oh, it slows down from 3 times 10 to the 8 to 2 times 10 to the 8 meters per second. It slows down quite a bit. And the wavelength changes by quite a bit, 300 nanometers to 200 nanometers. A few others that you'll use in the class as we move along here. Water is a good one. N of water is about 1.33. And N of oil is like 1.5. Those are rough. Problems will give you a number if they want to give you a number. They'll make up numbers, So basically between 1 and 1.5. You can get exotic materials. You can get it up to 2, stuff like that. Okay? That's just what happens. We won't get into why, but that happens. Okay. Happy. Okay. This one's really happy. So light is partially, and we also should say weakly, reflected at a dielectric interface. Dielectric interface. We will do some math soon, I promise. Just got to get these basic facts laid out, right? Okay, so let's draw what that would look like. So I said here, what we said here is when the light goes into a dielectric, it'll change its properties, but in addition, it'll bounce off the surface, or some of it will. So let's imagine here that we've got like a big piece of glass, and here I've got some light that's about to go in. Okay, I drew it backwards. It goes this way. All right, light's going into the glass. Basically, it will continue into the glass. Okay. The wavelength got a little shorter. I didn't make it. I could have made it look. Let me exaggerate it. There you go. The wavelength gets shorter, and it slows down. But at the same time, some of the light will, a little bit of the light will bounce back, like that. Okay. So you always get a reflection at any dielectric interface. And actually, it would also happen on the other side. So if we say, what if the light comes out of the glass? It'll come out and go back to its long wavelength, but a little bit will reflect. So you always get a reflection at any dielectric interface, from a low index to a high index, or from a high to a low. So in problems, you'll see it written like this. N equals 1, N equals 1.5, that's the glass. N equals 1.5, N equals 1. So you can see these are two different kinds of reflections. This is from low to high, and this is from high to low. We call this an external reflection sometimes. We call this an internal reflection sometimes. All right. Just facts. Let's see. Okay. Now here's the big one for interference that we're going to talk about. Okay. And then we'll be done with them. Then I'll prove them to you. Let's see. So reflection at a higher N causes a pi phase shift. Pi phase shift. So you can imagine that's going to be important for when we're thinking about, do these two beams reflect or do these two beams interfere or not? One reflected, one didn't. Maybe, because you get a pi phase shift. And if you look, I drew it here, sort of. I meant to. Here it was high. Here I drew it low. So I drew them out of phase. I didn't get their wavelengths to match that well, but you get the idea. I drew them out of phase. Right? So reflection at higher N causes pi phase shift. And you can imagine, then what's the other case? Reflection at lower N, so from like glass to air, causes how much? 2 pi. No, 0. Causes zero, no phase shift. And I attempted to draw that here. So here you can see it was low, and I had it come back still low. Right? We're at the same phase in the sinusoid. Okay? Those are just things that are true. Okay? That's what happens to light when it bounces around. That's the stuff we need to know. Let me prove it to you real quick. Oh, that's wrong mood music going here. I'm just going to show you a quick video of a string doing this. So you may have heard this before. That, oh yeah, let's see, I can show you that. If we ever have like a string wave bounce off of a rod, people will show you, oh, the rod, the string inverted, right? Like you'll see, oh, come on. Here we go. Sometimes you'll see if you're even watching, when I was sending pulses down that string that was connected to the rod, if I sent the pulse up, the pulse bounced back down. And that's basically was this. Reflection at a higher index N causes a pi phase shift, right? If it's up and it flips to down, if it were a sinusoid, that's like it flipping from up to down. That's like pi. But here's something we put together one year, because to me, a string versus a pole isn't very convincing, right? I mean, what does index mean? Index is kind of how dense the material is. A pole was very dense for a string, right? It's like an infinitely dense string. So here is one string here, and then a density of 4 strings here. So we're increasing the mu, the kilograms per meter, by 4, and you can see the reflection will come back with a negative interface. You see it went back to the left negative. Here's a better shot from the side. Here it is. And inverted coming back. See, always inverted coming back. Always upright when it goes through. Inverted coming back. If we could have, oh, who's that? It would have been nice to send a pulse here and show that there's no phase shift there. So we showed you this case, a pi phase shift, inverted, nothing here. Why didn't we flip the string around and shoot it the other way? I don't remember. Either we forgot, or it didn't work, or I was hungry and wanted to go to lunch. I don't remember what it was. Some reason we didn't. But if we flipped it the other way and sent the pulse from high to low, there wouldn't have been a phase shift. Okay, it would not have inverted. I could go get it. No, it's not. That would waste all kinds of class time. Okay. So that's the happy facts about light. Okay, so now what we're going to do is combine that with what we've been learning about interference. All right, here we go. And see what kind of problems we can solve if we know that. Let's see. All right, so we're going to do this by thinking about bubbles. Yes. You know what I'm talking about. The colorful, beautiful bubbles, you blow them, and they're thin, and they're all colorful, etc. We'll look at some later. But first, let's just do the physics. That's what we're more excited about. So we're going to combine the 6 facts we saw with a thin soap film, basically, and see if we can understand why bubbles are colorful. Soap bubbles are colorful, okay? Okay, so let's see. So here is the thin soap film. We'll just draw it as a slab. We love the word slab in physics like that, okay? So this is the soap film. It has some thickness T, like that. And of course, in the soap film, the reason it's different is it has an index of 1. I think we're using, it just has an index N. Okay, we'll just call it N. So a lot of times in these problems, if it's something in the air, you don't even say the index out here. It's just 1 here, and you just put an N there. And you know that this N will be higher. This must be 1.33 or 1.5 or whatever soap is. So if you're being super thorough, you'd always say N of air, N of soap. But I'm going to get you used to not being so thorough, like real problems will do. This has some N. It's obviously different from air, right? So, okay, so here you're inside the soap, here you're not inside the soap. Okay. So let's think about what a wave is going to do. Let's say I'm going to draw it at an angle. What we're going to calculate isn't really at an angle, but if I don't draw it at an angle, everything's on top of itself and you can't see anything, okay? So I'll draw it at an angle, and I will comment about angles later, all right? So what's going to happen is you're going to have a wave coming in of light. All right, so the bubble's floating in the room. There's clearly light hitting the bubble. It's going to bounce off the bubble and into your eye, and we want to know what is interference going to do. So some of the light will go straight in like that. Some of the light will go straight through, right? The bubble is transparent, right? You can see through it. But you're going to get reflections at every dielectric interface. So you're going to get a reflection here, and I can even try to draw it properly. This would be a pi phase shifting reflection, right? Because we're going from low to high, 1 to 1.33. So I'll try to draw that one going, instead of being down on the sinusoid, it'd be up on the sinusoid, like that. This one goes through, and this reflection, let's see, it's going to be no pi phase shift. Because it is from a lower to a higher. Reflection from a lower N. Wait, did I write that backwards? Oh, I said at and from. Wait a minute. Reflection at a higher N means into a higher N. Reflection at, there we go, at the lower N causes no phase shift. So that's what's happening here. A reflection at a lower N. Here we're at 1.3 for water, and then here we're at air. Right. Okay, so no pi phase shift here. So I draw it like that, okay? So we're trying to study the interference between these two, right? This is what gets to your eye. You got some here, we'll call this 1, and you got some here, we'll call this 2, right? Coming at your eye. And we just want to ask the question, is it going to be constructive, destructive? Maybe it's constructive for some colors and destructive for other colors, right? That would probably be the reason that the bubble is a special color. I mean, that is the reason. Okay, so how do we get the interference between two waves? We calculate the phase shift. Or the phase difference between the two waves, delta phi. And it's the exact same formula we've been using. Okay, so I want to make it clear. There's nothing really that different. We're just going to plug different things into it. Okay, so 2 pi times delta x over lambda plus delta phi naught. Exact same formula as for the sound. We just got to think about what goes in there. Okay, so let's see, what is lambda here? Lambda is the wavelength. So we got to decide, is that the vacuum wavelength or is that the wavelength in the film? Because remember, it changes. Yeah? I didn't really draw it changing that much, did I? I should have made it more compressed in here, but there's a limit to how much I care, I guess. So I should have compressed that. Okay. But there are two different lambdas. So the one that matters is the one that's telling you how many cycles does it go through. As it goes through delta x, well, it must be the wavelength in here. Right? If we're trying to keep up with cycles in here, it must be the wavelength in here. So this lambda, I did it correctly. I didn't put a naught on it. That really is the wavelength in the material. So lambda in the film, because that's where the difference is happening between these two. It's because it traveled in the film. So you could say this, then we could write it as lambda naught over n, okay? Because, like I said before, we don't ever like to talk about the wavelength in the material, because it always gets confusing. We always talk about the vacuum wavelength. So if we write an equation like this, we normally wouldn't put lambda there. We would put lambda naught over n there. Right? That's the difference. And what about this? What about this thing here? Before, we said that refers to a difference in like the phase constants of the source. So whenever we said two speakers are operating in phase, then we said that's 0. And sometimes we give you a problem and say two speakers are operating out of phase. You say, okay, it's pi. But then there was nothing that could happen to the sound that would suddenly make it change its phase, right? That would never happen. Well, it does. We just didn't talk about it. Well, now we have something that can happen, okay? So now that term is responsible for more than just the source phase. It's responsible for any reflections that cause a difference in phase. Okay? So this now includes delta phi due to reflections. We got to put those in. Okay. So technically when sound bounces off the wall, it might go through a phase shift. We just didn't want to get into it. So now we're getting into it. Let's see. Okay, so now with all that information, we can start to actually plug in and see what we get. Let's see, what are we doing here? We're combining 6 facts. Let's plug in. Let's say delta phi, or the phase difference, and let's put a label on it from 1 to 2. Remember, we're talking about the difference between these two waves, 1 and 2. It's 2 pi, right? 2 pi delta x. So this is where you can, if you have differences in distance and in phase, then you do have to keep 1 and 2 straight, so you get the negative signs right. So I usually like to do 2 minus 1. Okay? So let's see, how much farther does this one go than this one? 2t. Right, remember, the angle is just for the drawing. It's really just going in and out. So we put 2t up here. And how far does this one go? 0, minus 0. So if you really want to write it as a distance, you would say, to get from here to coming out, this one goes 2t and this one goes nothing. So that's the difference, 2t. 2t minus 0, final minus initial. Excellent. I was getting tired of talking. How did you get 2t? Okay, maybe you probably texted that before I said it. Yeah, because the light goes through there twice. Okay. Let's see. Where is the interference occurring? Inside or outside the film? Ooh, good question. Interference doesn't occur somewhere. Interference occurs between two things. So the interference is, so you're right. There's a way to say it. The interference is occurring here, right? This ray never got inside. I'm sorry, not ray. This wave never went inside the glass, so it's not interfering. But it can't interfere with itself. It can, whatever. This one did go through the glass, so I would say the interference is occurring out here. If we get into the photon picture, the interference is occurring everywhere, because all photons take every path through the universe all the time. But let's not, like I said, let's not do the photons. Okay, so there's that. And what do we put here? I said, we put that, but let's call it lambda naught over n. And because you guys are so good at algebra, such high SAT scores, I'm going to go ahead and put the n on top. Okay? I think you can handle that. Oh, I guess not. Okay. Isn't it more than t because it's at an angle? The angle is just for you to be able to see it. Right? There's no angle here. It's normal. But if I drew this without the angle, I'll do it if you want me to. Here we go, and then this one goes in here, and then it comes back here. Look, interference! Okay. So the angle is just so that you can see the drawing. We'll talk about the angle later, maybe. If it's 1 to 2, shouldn't it be 0 minus 2? No, because I made 2 go through the film. 2t. There's your 2t right there. I do actually prepare this ahead of time and check things like that. All right. Why t? Because I could use any letter. Jesus. Okay. So t is the thickness of the film. Wow, okay. T is the thickness of the film, right? So that's the path that went through farther. Where did the n come from on the delta x? Oh yeah, the delta x became this. It's really lambda, okay, y'all are screwing with me now, right? It's really lambda naught over n, okay? Because it's lambda naught over n, because remember this lambda is lambda naught over n. Okay. It must be college night. Okay, why do you, no, just kidding. There's nothing wrong with being confused. This is very difficult. I'm just having a good time with you guys. Why do you use lambda of the film wavelength? Because, oh, sorry. These are good questions. Why do you use lambda of the film wavelength? Because 2 is outside. Okay, so I think I needed to do my hash marks here. This is the film. Maybe some people don't see the film. This is the film. 2 went like that. 2 is the one that went in the film. See? It went through the film twice, 2t. 1 did not go through the film. So I think it's that my drawing is confusing. Yeah. Okay. That's how we came to this. We haven't done the phase yet. Okay, let's do the phase. The change in phi naught, they have the same phi naught, they have the same phase constant because they came from the same wave. So like when you say the 2 speakers are in phase, this is like it was 1 speaker. It has to be in phase with itself. But one of them went through a phase shift. The one that never entered the glass, that saw an external reflection here, picked up a phase shift. You can call it pi or you can call it negative pi. I'm going to call it, looks like I called it pi. I usually just write a little plus pi on that one, just to remind myself. It went through a phase shift of plus pi. Why does a phase or phase difference actually communicate? What does, oh, we're going to see. I'm going to physically show you. Somebody's asking, why are we calculating this? What's it going to tell us? You'll see. So this went through pi. This went through 0 phase shift. I like to draw my little phase shifts as a little number on the wave just to help me keep up. Okay? So 2 minus 1 would be 0 minus pi. All right? So we ended up with all that. And now, here, why does this matter? What is it going to tell us? What are we going to set this equal to? This is the thing that tells us if we get constructive or destructive interference. Right? Oh, yes, I'll get to you in a minute. So what we're going to do is we're going to say, where is it constructive? Where will we get 2 pi m constructive? Right? So for the person who asks, what does this all mean? This is all telling us for what combination of wavelength and thickness are we going to see constructive interference, and therefore that color is going to be bright. Right? If the answer is for red light, it equals 2 pi m, then this is going to look red. But if we move the wavelength a little bit, we'll be to something where it doesn't equal 2 pi m. It'll be deconstructive if it's 1 pi m. So it might be that it bounces a lot of red due to interference, constructive, but it doesn't bounce any yellow because of destructive interference. And that's why the bubble looks red. Okay, that's why we're doing this. And somebody asked, so I think I've confused you with the bullets and all this, but let's go through it real slow and careful. But doesn't 2 go into a higher n? Yes. You're with me. It's 2 that went through the 2t, but when you're asking why doesn't that get the phase shift, is the phase shift depends on the reflection. Okay? Only one had a reflection at a higher n. I think that's the wording that's confusing. When you have a reflection at a higher n, you never went into the higher n. Right? That's why this one has no, or one has the pi phase shift, is it never went into the higher n, it just reflected at the higher n. And the other one says a reflection at a lower n. That's 2. Nothing happens when you go in, but it reflected off the back at a lower n. So it had no pi phase shift. Yeah, you want to get it all straight. Because, you can get by with just the formula, but you don't do that. Okay, I'm so confused. I know. I'm sorry. So the book, that's what the book is for. This is kind of introducing you to the idea. If you don't follow this lecture, you're like, well, I have some idea what's going on. Now when I read the book, it'll make more sense. So read the book, 13 hours. Okay, let's keep it together. Let's simplify some stuff. Pi goes away. Yeah. 2 times 2 is 4t. 4 times the thickness, minus 0, doesn't matter. I'm going to put the n up here now, over lambda naught. All right, that term turned into that. Then I'm going to say that's a minus 1, now that I canceled the pi. I'll just bring it over here as a plus 1. And I got 2m plus 1. All right, that's like the answer. That's the condition for constructive interference. I'll write it like I'll write that phrase. This is the condition for constructive interference in a film. A certain kind of film. It'll matter if it's like a soap bubble or a film on glass. We'll get into that in a minute. What's the thing under the squiggly in the parentheses? Oh, thing under the squiggly and the parentheses. That's the only squiggly. I don't know. Ask me after class. I'll look at your notes with you. Oh, wow. Yeah. Okay, yeah. So I'm sorry. Just hang in there. That's all I can say at this point. We went from n equals 1 to n equals 3, n equals 1. This is a reflection at a higher n. This is a reflection at a lower n. This one went into the n. I mean, I think at this point I'm not going to just sit here and ramble. Okay, so if you're totally lost, come to office hours, read the book. Okay, I'm sorry this was so confusing. Let's see. Where is the 2 pi from? Again, the 2 pi is because we're doing constructive interference. So they have to come out in phase. Which n value is used in the equation? It's the n of the soap film. Why would one wave be reflected at higher n and the other at lower n? Just follow the n's. So we see colors when there's constructive interference. Oh my God. Yeah, yes, okay. Okay, all that done. Let me just now show you the next slide. I think it'll actually probably help more than it'll hurt. It couldn't be worse. Okay, I'm definitely not going to do that. We're not doing that. Are you kidding me? No, that'll make it worse. Oh my God, okay. Okay. This went well. Let's put some numbers together here and just see what we get. I think it's worth plugging in a couple things here, see what we get for a typical soap film, just to prove to you that there would end up being colors, and that'll be good enough. So let's say T equals 500 nanometers. That's like the thickness of the film, okay? Half a micron, a few wavelengths of light, right? And let's say N, I'll give you a value if you want a value, was 1.33, right? A soap solution is basically water, so it's basically the value of water. If you now go through and start calculating these, like let's say m equals 1, right? What would that look like? You'd say, well, lambda 1 then. You'd plug in and you'd say, well, it's 4 times 500 times 1.33 over 2 times m plus 1, or well, 2 times 1 plus 1, which is, 2 times 1 plus 1, right, which is 3, right? So you do all that, and you're going to get it 887 nanometers. So that's constructive interference. Everything we're doing here is constructive interference. It'll be really bright at 887 nanometers. Can you see 887 nanometers? No. Okay, that's not in the visible. So if we take these typical soap conditions, maybe we go to m equals 2. All right, m equals 2, do the same thing. You get lambda 2 equals 532 nanometers. That's green. You can see that. All right, and then you do m equals 3. And you say, oh, m equals 3, you get lambda equals 380 nanometers. Actually, you can't see that. Well, you probably could if you shined enough in your face, okay? But that's just below what you can see. So that's just below blue. So if we were to make a spectrum here, a plot for wavelength and what you see, I, intensity, right? You'd say, here's 400 nanometers, the edge of what I can see. Here's 700, the edge of what I can see. And you can say, where is it constructive? 532, right here in the green. Where is it constructive again? 887, way out here, I can't see it. And right there at 380. Right? Where is it destructive? Well, maybe you've thought about waves cramming in and being out of phase enough, you would know it's going to be in between. Right? So it's constructive here, it's destructive here, it's constructive here, it's destructive here, it's constructive. So like in the visible, you see a lot of green and things near green, but in the red and the blue, you don't see it. Okay? So that's why it looks like a color. All right? Yeah. So what we'll do is during the break, I had 2 things. We had a survey. The survey can wait, but we'll look at the colors. Everything has been turned into a show, is what I've learned about the universe. Nothing cannot be a show. So we'll do the break, and if you're bored, you can watch this. Where is it? It's a little better than my video, I have to admit. Bubbles have been turned into art. It's awesome. I'll turn it down. Oh my God. It's very exciting. Although you don't have to listen. You can talk amongst yourselves. Okay, 5 minutes. We'll continue the clarity. Oh, yeah. It was just intensity. Yeah, just kind of what you would see. Yeah. Okay. know what's a little risky is I didn't really watch this whole thing ahead of time. So fortunately, it stayed at least PG, I think. I don't know. Yeah, I don't have this on. Okay, when I looked at my notes for this lecture, the last thing said they were really confused about the bubble. And I was like, yeah, but I was probably drunk when I gave that one. This one, it was probably something I did. And I realized, no, this is just fundamentally more confusing than I thought it was. So based on people's questions after class, or during the break, I think I'm going to try to fix it and re-explain it all. But here's a few little things that people ask that I think might help is, we're talking about certain wavelengths being constructive and destructive. Well, first of all, that's what this is, right? This makes it constructive. You could put in 2 pi m plus a half, or 2 pi 2m plus a half, whatever it is, and that'd be the destructive. So we were just solving for, in a problem, it'd say, here's a film with this thickness and this index. For what wavelength do you get constructive interference on the reflection? And that's what this formula would tell you, right? You would say you'd put 1 in here, you'd put in the thickness and the index, you'd solve for lambda. Or you could use this to where if it says, I have light at this wavelength, what thickness of a film will give you constructive interference? So you'd solve for T. So we're just setting this up as a general equation you can use to find wavelengths or thicknesses. Okay? And the idea is that what happens in reality in the gazillion light person is white light is going onto the film. Right? White light contains all colors. So instead of the white light reflecting back, some colors reflect back because they constructively interfere. Some colors don't reflect back because they destructively interfere. Okay? So really you can do all the wavelengths at once. We just set it up for one wavelength. If we did the full thing as a function of angle, we would find that also the constructive or destructive depends on what angle you look at. So people asking, isn't this path difference different for the angle? The answer is yes. We could do that, but it's actually a lot harder than just one triangle. Believe it or not. As you make the angle bigger, the path difference gets smaller. Yeah, it's a lot of geometry. It's not worth it. And then people are asking, won't it really bounce like this? And yes. And like this, and like this, and like this, forever and forever and forever. That'll all happen. So it will bounce back and forth a whole lot. Okay. This is used, and then another person, excellent question, when I said, oh, this will work for this film. So what does this work for? This works for a soap bubble. Does it work for anything else? Yeah, it works for any film where we have a low index, high index, low index. All right? But most films you encounter in your everyday life are not like that. Just say a teeny bit about this, and then I'll show you the pictures, and then we'll move on to double slit, which is easier. We did a soap film, and it was critical in that description that it went from low index to high index to low index, right? Because that's what told us the phase shifts, right? We said, okay, this one bounces, this one goes in and bounces. So this was, let me write it, n equals 1, n equals 1.3. It was just that, right? So this one went through pi phase shift. This one didn't because it was from low to high. But another use of these that's very important is anti-reflection coatings. So who has glasses? I don't need glasses. And glasses would reflect a lot of light, but they put a film on them that makes the reflections go away. Right? So here are happy people that had an anti-reflection coating added to their glasses. Okay? So it would look something like this. They put a film on the glass. So now you've got n equals 1 is air. You've got n equals, the film is like 1.3 magnesium fluoride. If we can get into a little chemistry here, that's probably wrong. And then you've got to put it on something. Right? You can't just have a bubble in front of your eye. Right? Then you have to actually have glass here. So n equals 1.5 for the glass. So let's think what we've done is the light comes in, bounces, some of it goes in, and bounces and comes out. And we're going to interfere these. Right? The first ray had what phase shift? Pi, because it went from 1 to 1.3. But now that there's glass on the other side, this one also had a pi phase shift. Right? They both have a pi phase shift. So that's why the pattern and what you would get would be completely different between the two. But between a soap bubble and an interference film on glass, there's just a half in the formula difference somewhere. Okay? This is actually done in section back in the chapter 17. There's a little description of how to make an anti-reflection coating. So you can look at that if you want, but it's way before what we just talked about. This is also used other ways. Let's see. So here's some glasses people. More glasses people. See how much better you look after? I like this one because it looks like Dr. Cone. Did anybody take 101? It looks like Dr. Cone. And then this is like a sick pair of glasses here. It's like they only put it on one because she couldn't afford to put it on both, so she only put it on one. Let's see. In that first drawing, are they both reflected with pi? Why are they both with pi? So you got to look at these numbers. Here, let's make a plot. Let's make a plot. I'm getting worried. Let's make a plot of index. Here we go. This is space. This is n. Okay? This is 1. And this is 1.5. What is the index? 1, 1, 1, 1, 1, 1, 1, 1, 1.3. 1.3, 1.3, 1.3, 1.3, 1.3, 1.5. 1.5 into the glass. Okay? This first reflection was at an increase in the index, so it had a pi phase shift. This reflection, increase in index. They're both at an increase in index. They both have a pi phase shift. The bubble would have been up and then down, right? Are there different m's referring to a starting wave? The different m's, okay, so if we wanted to talk about, this is getting a little more advanced than we're going to do. But you could put in m equals 0 for constructive, m equals 1 for constructive, m equals 2 for constructive. This is the extra thing I was going to draw. You're just cramming different numbers of waves in the film. Right? I could make it really short and it could still come out constructive, or I could make it really long and it could come out constructive. That's m equals 0, m equals 1, m equals 2. Okay? That's why you can have different wavelengths come off. Yeah?
Should that pi be 0 on the n equals 1, n equals 1.3, n equals 1? Because it goes like pi.
Oh, I wrote it on the wrong one. Okay, that's why people were confused. Yeah. There we go. Thought I was writing over here. Yeah, there we go. All the questions were because of that. There were 0 mistakes in the first half of the class. Yeah, okay. A lot of people are pointing that out. Let's see what else we got. Oh, we have art. This is also used in art. Okay? Let me find something white and show you if you put these films, a white background is what I'm saying here. If you take these films and you put it on a piece of glass, you can look at what it reflects and what it transmits. Let me get really close to the white light here. So this is a film from an art installation that was here called Unwoven Light by Sue Sunny Park. Long before you were like in middle school or something, right? And she had all these films, and they're thin films that cause these optical effects. And it changes with angles. So here you can see oh, look at that. It goes from purple all the way like that, right? So she had thousands of them all together, and I gave a talk about it, and they took out all the dirty jokes on the YouTube channel, so I was annoyed. But anyway, whatever. They made it very G. And it's very similar to this. So some people think it's good to combine art and science, and it's actually really not a good idea. It leads to bad things. STEAM, you know. So there's this company that will sell you for a lot of money huge panels made of this kind of material, this dichroic material as it's called, which is a misnomer, okay? And what you're supposed to do is you're supposed to look through it. And when you look through it, it'll blow your mind. Everything is different colors at different angles, and you look out the window, and it's like, you know, you're on some substance or something. It's amazing as you walk by. So the physics department got together with some artists and said, let's spend God knows how much money on this and buy these giant panels that you walk by on your way to Gen Chem. And they put them in front of a white wall. You can't see any light going through them. All you see, because of the way they're made, you don't even get the reflection thing that much. You mostly just see the gold of the gold film they used. They should be on the windows, not on this white wall. And every time I see it, I just get so mad. I'm just like, oh, this is so stupid. Why is this? Why? It was like, they spent the money. We could have, every time people walk by Brockman, to be like, that's the coolest thing I've ever seen in my life. And instead, we have basically tinfoil on the wall. So, whatever. I'm serious, my blood pressure, every time I walk by that wall, I get angry. It's like, ah! Okay, so that was films. It was a little confusing. Read the book, come to office hours. It'll be okay. It's not as bad as it seems the first time you see it, we'll say. Okay. Oh, God. Yeah. Okay, now we're going to do the classic. This is how the wave properties of light were first discovered. Young's double slit. right? So Young means the person. Young, Ernst and Young, I don't remember his name, something Young, Thomas Young. And what he did is he shined light through two slits and saw an interesting pattern at the other end of the room. And it's actually, historically, he had to shine it through three slits. Okay, it should be Young's triple slit, but only the two of the slits are important. So we call it Young's double slit. So I'm going to draw it. Okay, so everybody will be okay. I'm going to draw it. Hang in there. Here we go. We're looking down on the slits, right? There's slits and we're like this. Okay, so when I say there's a slit, I mean that it is this way. We're seeing the very small width of the slit, but it's like there's the slit right there. Okay, so I'll draw little marks on this. This is opaque. The light is not going to go into this. Okay, this is like metal. Okay, a dielectric literally means dia means through, and electric means the electric field. The electric field can go through it. Dielectric. This is a metal. Light can't go through the metal. Okay, so it's totally blocking the light. We're going to shine light on this, and we're going to shine a plane wave, which sometimes you might see drawn like this. Okay, this is a representation kind of like we did for circular waves, where we drew the circles, the concentric circles that were so beautiful. Those meant the peak of the wave. Same thing here. That's all this means. We could, actually draw the wave if we wanted to, like this. It'd look like that. So the wave, it's a plane wave. It's got the same amplitude everywhere, and it's going through like this. So you can see some of the light is going to go through the slits. Okay? And what's interesting and fascinating is what happens out here on the screen. All right? This was all named before modern technology, so it's called a screen, not a camera or film or anything like that. Okay, that's all going to happen. And then it's good to sort of just define something as 0. So I like to draw this line right here just to help guide your eye. Right between the two slits, we call that, like the origin or the center. And then we say, what else is going to happen? And the question is, what's the light going to do on the screen? Right? Is it going to make some pattern that indicates it's a wave? What's it going to do? Okay, so a few bullets here. So it's two sources, and the sources are in phase. Right? So just like two speakers that we say are driven by the same power supply, they're both in phase. These are in phase because it's really one light wave. And of course, it has to be in phase with itself. So it's starting with the same phase here. Okay? So the good thing about Young's double slit is there's no delta phi naught to deal with. Right? Well, we might find a way, but there isn't usually. Okay. And you just consider path difference. Right? Okay. And we look and say at the center, let's start by predicting what will we have at the center. Will we have constructive or destructive interference? Think about it for 30 seconds. No, you don't need 30 seconds. You'll get it right or wrong in 15 seconds. Think about it for 15 seconds. At the center, are we going to have constructive or destructive interference? Let's do a 1, 2, 3 and say the word constructive or destructive. 1, 2, 3. Constructive. Everybody knew, but they didn't want to be the first. Everybody's like, 1, 2, 3. Constructive. Okay. And it's just like the sound things we did. The distance from here to here and the distance from here to here is the same. Right? So they started in phase, and they wiggled in phase, and they went the exact same distance. They're going to arrive in phase. Okay? So at the center, delta R equals 0. This is technically like a 2D problem, so we'll call it delta R instead of delta X. 0, so they're in phase, so it's constructive. But elsewhere, what is it? That's what Young's double slit is about. What is it as we move up and down the thing? So I know we can do it. Let's see. Oh, dear. Let's see. All right. Okay, so what are we going to do? Let's see. So I'm going to end up drawing this a few times because it has too much junk on it. So let's draw it again. Here we go, without all that wiggly stuff on it. And we'll make it a little bit bigger to make it easier to see things. Right. Yeah. Well, I guess the one drawing you might add that helps a little bit is we're going to say, what is it elsewhere? So let's say, how about here at some point P? So how would you figure that out? Well, you would just draw a line from this slit to P and from this slit to P. Right? So what I want you to visually see there is they're no longer the same length, are they? Right? They're now different. So we just have to do some geometry to figure out what's the difference and how does it relate to lambda and all the variables. Right? That's all we're doing in Young's double slit. It's actually a lot easier even than the films. There's really less to it. Except we have to make approximations. Okay. So we're going to call this D. D is the separation between the slits, and we're going to call this L. L is the distance to the screen. Here we go. Like that. D and L, like that. Perp to R2, yeah. Okay, and then we're going to pick a point up here, and we're going to say we want to know the intensity there. We know the intensity here. Here's the center. Right, but we want the intensity there. So we're going to draw this again. And we're just drawing it again just to have less stuff in the way. Like that. Okay. Yeah, let's see. Okay, let's see. So how do we get the difference in these? Okay, so we need difference. So let's go ahead and label them. This is slit 1, this is slit 2, this is R1, this is R2. All right. So we know that for interference, we need the difference in phase between 1 and 2. Right? We know it's delta R between 1 and 2 over lambda times 2 pi plus delta phi naught. Right? And that equals 2 m pi if it's constructive. So that's just like the bubble. Right? But it's a little easier now because what is delta phi naught? 0. Right? They were in phase here, so they're both at 0. They didn't reflect off of anything. They didn't go through any dielectrics. Nothing happens. This is just 0. Good. That helps. So we're really just down to this thing. How can we make the difference in R over lambda times 2 pi equal some integer multiples of 2 pi? 0, 1, 2, like that. Right? And so we look at it, and one way we could just do like lots of Pythagorean theorem. Pythag overload would be one way. And we wouldn't really get any insight. Okay? You can take every problem and figure out the exact geometry and do the square root of this squared plus that squared is that one, square root of this squared plus that squared is that one, subtract them, and it'll be just a big numerical mess. You won't learn anything. Okay? So we have to do approximations. Okay? We don't want to do that. So instead, use approximations and assumptions. All right, so I have one of these set up here, okay? The slits are very close together. And when we see the effect, we see it very far away, right? It's going to be on that wall over there. Okay? So what we know here is that L is much, much bigger than D. Okay? L is much, much bigger than D. Doesn't have to be. I could put the screen right here. But then I'm doing a different kind of a problem, and you can't see it. Okay, so that's advanced optics. That's near field optics. We're doing far field optics. Okay, so what we got to say is the difference. What you really do is you draw a line right here, perpendicular from R1, where R1 starts, to where R2 goes. All right, so there's your delta R right there. Delta R, 1, 2. But we need a mathematical expression for it, right? I mean, it's nice to draw it. So instead of all the Pythagorean calculations, you could get out your ruler, and we could measure it, right? I have a yardstick there. We could actually measure it. But we need, using these approximations, we want to come up with a simple formula for it, right? Because that's what we do in physics. We come up with simple, intuitive, obvious formulas like that. Everybody knows exactly what we mean. So let's see. All right, let's see. So let's draw it a little bit real world. Let's get real for a minute here. And what it really looks like is this. There's the slits right there, and here's the screen. and here is R1, and here is R2, right? In reality, you can't even see the two. It's totally on top of each other. So what we're trying to learn from this is they're actually all at the same angle. All at approximately the same theta, okay? So if they're all at the same angle, and if you do a little geometry, you can actually convince yourself that that angle is this angle. Okay, that's theta. So you can calculate theta basically from how high you go on the screen over how far you go L. And really all three of these are going at that same angle. And then if you draw something perpendicular here, you'd find that that is theta. It's all the same angle because we have L so much bigger than D. Okay? I mean, I'm not going to do the geometrical proof, okay? So you just have to believe me on that, okay? Okay, that's all the same angle. Then you say, okay, if L is greater than D, that theta is small, right? That's what you want to say. So then we just start doing geometry to figure out what that theta is, because that theta is the key to getting delta R, right? If we know this angle, and we know that this is D, then we just use like a sine or a cosine or a tangent, and we have delta R, right? That's where we're headed here, this approximation. Okay, so we say if it's small, then what does tangent theta equal? Well, tangent theta equals sine over cosine, not just because it's small, right? But what is sine theta for small angles? Theta, right? Sine theta equals theta. Believe it or not. Put 0.001 in your calculator, and then take the sine of it, and you'll get 0.001 back. Right? It is. You really will. Sine theta is theta. What is cosine theta for small angles? 1. Put 0.001 in your calculator and hit cosine. You'll get 1. So tangent theta actually also equals theta for small angles. Right? So tangent theta is just theta in radians. Right? This is one of those you got to do it for yourself to really believe it. So I know you want to believe it. So this is just a way to get theta from the geometry. Then what is theta? Well, we're up here at some height y. We're trying to get the intensity as a function of height y. So it's just y over L, right? Where here's L. Right? Because it's like a circle. It's like a big circle. What's theta? S equals theta r. Right? So y is like the arc length. And L is like r. So S is like, what have I done here? Y is the arc length, S, oh wait, no, let's see. Y is S, and S equals theta r, never mind. So we would say Y equals L theta, right? S equals theta r, right? So for small angles, that's going to be true, okay? Sorry about that, that was confusing. Okay, so now what can we do? We just have made this, we sort of said it's that, and we've made this geometrical approximations. Now we just got to combine them somehow. Let's see if we can combine them in a useful way here. You can look at it and say, let's go back up here and say, let's get delta R12. I've gone off my notes now. Let's see. It looks like it's d tangent theta, right? Because it's opposite over adjacent. Yeah, it's opposite over, it's d sine theta. All right. Delta R is, well, I'm doing this totally different. Delta R is d sine theta. Is that right? Yeah, we have the separation there. Sine is opposite over hypotenuse. Yes, d sine theta. Okay. All right. So what is sine theta? Well, sine theta is just theta. Sine theta is y over L. All right. So delta R 1 to 2 equals dy over L. So the point is for small angles, it just becomes a little algebraic expression. It doesn't, it's not a big mess anymore. All right. And then we take this and we plug it in, and I've done it in a different order. Hopefully it comes out right, to the phase condition. Delta phi 1 to 2. All right. Delta phi 1, 2 equals, let's see, what was delta R? It's this, dy over L. And in the bottom we have lambda times 2 pi equals what? 2 pi m. 2 pi m. All right, the 2 pi's go away. And you basically get a simple relationship. Where did L go? What did I do? My L is not supposed to be there. Oh, I have it in terms of theta. Here we go. There it is. Okay. So we solve this now for y, right? So we're just we want to know what is the height of a maximum, right? So these are maxima because we set it for constructive interference, right? We made it constructive when we said that, 2 pi m. So y max should be m lambda L over d. Yeah, m lambda L over d. All right. So that was weird. It was just doing a few geometrical approximations to figure out where is this going to be a maximum. Okay? Is that all we do? Let's see. Oh, yeah. No, now we're going to see what it means. Okay. So let's see what this means. This is where the maxima are. Right, this is where the maxima are. So this is the answer, right? This is the answer for Young's double slit. But let's see what it means. So if we were to draw it again real quick, we could say, what's happening here? So now when we draw it, we don't draw it for the really long case. We draw it shorter so you can actually see it. Okay? So when they come in together, that's m equals 0. Right? They're coming in with the exact same, and they're showing up in phase. Right? But then m equals 1 basically means that you got one extra wavelength between them, right? So this comes in like that, and this, if you looked, it's like that's the difference, right? So it's got to go through an entire wave like that, trying to make it match like that. So that's why this is m equals 1, because we have one extra wave in between them, like there. See? What if we went even higher? What would that look like? Let's see. What if we went to m equals, or we go to a higher point, the next maximum would look like what? Let's look. Here, here, like this. So we have m equals 0. We don't care about that. M equals 1. We don't care about that. But here, let's look at m equals 2. Right? So m equals 2 is one ray is going to go like that. One is going to go like that. And there is the difference right there. So m equals 2 is another maximum where it goes through two waves. Right? And then it's in phase like that. And they show up in phase. What if we plug in m equals -1? Oh, it's just down here. That just has to do with if we define the y-axis positive up or the y-axis positive down. So what we found is the positions where you have constructive interference. Now, guess what's in between them? Is positions where you have destructive interference. Right? So if we were to look here in between 0 and 1, and you did this, right, and you drew the line, you'd find this is half wave. And that's why they would show up destructive. So in the end, you actually get a pattern that I think in the book we just give you the formula for it. We don't derive it. But we could actually do it for all y's, and it looks like this. Right. So if we look at the pattern, we get I on the screen, and this is in watts per meter squared. It's just the amplitude of a light wave. Same we talked about with other waves, just the power per unit area. It's just here it's light instead of sound. It equals actually 4, and then the I naught, this is the watts per meter squared on the slits, right? Whatever's coming out of the slit. And it actually follows a cosine squared, right? So if you did this with more full electromagnetic theory, you'd get cosine squared pi d over lambda Ly. Okay? And you could ask yourself, where is that going to be a maximum? Cosine squared is going to be a maximum every pi. Right? So when this is 0, that's a maximum. That's m equals 0. When this is pi, that's a maximum. That's m equals 1. And it would look something like this. Then you'd have your two slits like this, and the one at 0, and it just goes like this. Cosine squared looks like that. Always positive. Okay. So that's what Young saw. So let's see what it looks like. This is a little bit more than a laser pointer, so don't get up. Let's see, right. So here we have a laser beam just so we can have enough light. Hold on. Oh, there you go. You're fine. No, you'll be fine. Yeah, no, it's fine. I'm just kidding. It's really fine. Right, so here we have our laser beam going, and it's not going through anything. Right? It's just a little teeny piece of a plane wave going along. So this has two little double slits in it. Here you go. You confirm. Those are double slits, right? Say yes. Just say yes. Yes, thank you. It's two slits. Actually, you can't tell. If you want to look at it later, if you look really close, you can tell. So all I'm going to do is put them in the beam, and we'll see what pattern we get. Like this. There we go. And tweak it up a little bit. And look, it's kind of like a cosine squared. Or it's similar to that pattern. All we've done is send the beam through two slits. We didn't send the beam through a bunch of different slits. It's just two. And there's a spot, and there's a spot, and there's a spot. And it looks like it's following a cosine squared. So it really happens. What if we turn all the lights out? What else is happening? Let's see. Ooh, now look at it. It goes further, and if you look really close, if the sun weren't out, let's see, it goes like dim, and then it actually comes back again. And I can actually see it to here. And if you really could get the lights out, it goes, really far. So we could do, I guess I'll make a homework problem about it because we don't have time, is we could run the numbers and we would get the right wavelength, right? That's L. The D in this spacing on this thing is like 0.2 millimeters. So 0.2 millimeters D, like 15 or 10 meters L. And if we measured this delta Y, this is Y, and ran those numbers, you'd get the wavelength of the laser, which is 633 nanometers. Okay? Now, the last thing is what we'll talk about soon, next time probably, is the reason this doesn't look like cosine squared, does it? Because why is the amplitude dropping off? And why does it come back and then drop off again? Right? That says it should be cosine squared forever. Right? So we'll talk about why it's not cosine squared forever, why it dies out.